Okay, so we've talked about how to solve homogeneous and non-homogeneous problems, systems of differential equations at this point, right? But the one thing we really haven't talked about yet is how to solve a simple problem with piecewise discontinuities. And that brings us to the problem, well, to the technique of Laplace transforms. So the Laplace transformation, or the Laplace transform technique, allows us to solve problems that have discontinuities in the forcing function. So I'm gonna begin with an example, actually. And so, of course, I'm going to do things that don't make sense, but this is just to give you a flavor for how the Laplace transform works. So suppose we have something like y prime, well, let's say dy dt equals to, let's say, the unit step function of t minus 3. Now, this function, it's 0 for t less than 3, and it's 1 for t greater than 3. All right, it's the unit step function. And let's suppose, in addition, that we're given that y of time 0 is equal to 2. All right. So then here's the problem. Find y of t for t greater than or equal to 0. All right. Now, of course, you could do this with conventional calculus. What would you do? You break it into pieces. You solve dy dt equals to 0 from time 0 to time 3, right? So you could actually probably solve this without too much trouble. I mean, I think I can even write down the solution. So let's see here, y of t would be equal to, well, it's obvious that it's just 2 because dy dt is 0 from time 0 to time 3. Yeah. And then at time 3, it starts becoming dy dt equals to 1, right? dy dt equals to 1 is a t that has slope, so it has slope 1, it's constant slope 1 for all time. It's a linear, it's t, right? So you'd put t there. But let's see here, to make it continuous, if I want to, I'm going to say find a continuous solution. I suppose you could imagine finding solutions which were not continuous, right? But let's assume that our solution's continuous, which means it's got to paste together at that breaking point. So you can see then, so dy dt equals to 1 gives me t, but I got to add a constant. I should choose the constant so that it matches 2 when you plug in t equals to 3, minus 1, right? And there you go. Again, you put equality on both sides if you want. They match. But as you can see, even though this problem is fairly simple, it's still kind of a pain what we had to do, which is break up into cases. Now, when you look at more complicated differential equations, it gets worse, right? The problem of pasting together the solutions is really kind of a drag. All right, so the Laplace transform technique says it has step 1 is you take the Laplace transform, which we use this L symbol for, to convert, your given initial value problem to an usually algebraic problem in the frequency domain. That's borrowing some terminology from electrical engineering, but the traditional thing to use is the letter S for the transformed problem. Now, we'll derive this, but the Laplace transform of y prime as a function of S is, well, big Y, S times big Y, and then minus the initial condition y of 0. Now, big Y is the transformed Y. This is the Laplace transform of Y. And so that's S times big Y for us minus what? 2. Oh, I'm sorry, I seem to be writing in green. And then we also need to know what's the Laplace transform of u of t minus 3. Now that I don't remember right off the top of my head. So I'm going to derive it from the very definition of the Laplace transform, which is as follows. You take the integral from 0 to infinity of e to the minus st, the function that you're Laplace transforming, which in this case is u of t minus 3 dt. For this technique to work, the function that you stick into this integral, it must give you a convergent integral. That's going to be the case for this. So this is a very nice integral to do because it looks infinite, but it's not really because, oh, wait a minute. No, it really is. How can I simplify this to start with? This is the integral from what? From 3 to infinity of what? Yeah, because this is just 1, and it's 0 before that, so that just gives us this. But then I can anti-differentiate that. That's not a big deal. That's e to the minus st over, minus s. You got to evaluate that thing from 3 to infinity. So if t is positive, then that's t being infinity. Now if s is positive, rather, e to the minus infinity. If s is positive, s times infinity is positive. So this gives you e to the minus infinity. So we have e to the minus infinity over minus s plus e to the minus 3s over s. Of course, this goes to 0. I'm avoiding explicit. And so there you go. That's the Laplace transform of this. Okay, so to complete the thought for number 1, we have s times big Y minus 2 is equal to e to the minus 3s over s. All right? So now I have transformed the given differential equation from the time domain to the frequency domain. You notice that now the equation is algebraic. There's no derivatives in big Y and s. It's just an algebraic equation. So step 2, you do algebra. You solve for big S. For big Y. Now, there are differential equations that when you take the transform, you end up with differential equations in the S domain as well. But those are nasty examples, and they're less common, for the introductory course at least. So this gives us what? Y is equal to 2 over s, right, plus 1 over s squared, e to the minus 3s. All right? And now, step 3, we have to take the inverse Laplace transform. So L inverse of y gives you back a function of t, and so that gives you y of t. The other direction was versus the Laplace transform of little y gives you a function of s, which we denote big Y of s. All right? That's pretty standard notation. They use the big letters for the transform variable, dependent variable. Okay, so all right. So what's the inverse Laplace transform of this? Well, here's the part where it's kind of hard for you to appreciate, but I'm just going to have to tell you the answer because we haven't derived anything just yet. The inverse Laplace transform of this is just 2. And then the inverse Laplace transform of this is actually, so here I need a theorem. There's a theorem which says the inverse Laplace transform of, let's see, how's it go? F of s, e to the minus as, what is it equal to? The theorem says that is in fact equal to f of t minus a times u of t minus a. So here, the Laplace transform of little f is equal to big F, if you're wondering the relation between that and that. So for this problem here, this one, I need to know, okay, so basically my f of s, Bailey, are we getting this? I don't think so. big F of s, I think you need to move over. Big F of s is 1 over s squared. And where that comes from is the Laplace transform of t, I believe, is 1 over s squared. I don't know how you'd see that right now. I'm telling you. Unless you have some sort of bizarre intuition about knowing what Laplace transforms are, that would be shocking to me. That would be really, really, really weird. But anyway, so basically my f of t is t, so I have to put in here t minus what? T minus 3, and then times u of t minus 3. And there you go. That's the solution for all time. No breaking into cases. That's cool. And of course, though, we can take that and break back into cases, right? What does this give us? If you have t less than 3, this is 0, so you get 2. This assumes, the Laplace transforms assume, at least the way it's set up here, assumes that the domain of functions starts at 0. That's built in. And then if t is bigger than 3, this is 1, right? So you get t minus 3 plus 2, you get t minus 1, which of course is the same thing that we derived just through basic calculus and pasting things together. But I would point out to you that this is a far more elegant solution. And if there's not just one case, if we have 5 cases, right? If we're turning the switch on and off, and then 2 switches on and 1 switch on, I mean, we have like 5 different things switching on and off. We can do all like 5 or 6 cases that there might be all at once in one algebraic calculation with this technique. That's the beauty of it. Okay, so that's to give you, just to give you a motivating example before I get back into theory. So now I'm going to go show you the main theoretical results, give you the definition, so forth and so on. But that's why we're doing this, okay? So we can solve discontinuous problems.
So we can solve multiple cases, like a case of t, like t is less than 3, t is greater than 3.
Right, exactly. So we can solve them at the same time rather than breaking up. It's a little bit more than that. It also will allow us to treat something called the Dirac delta function, which is perhaps new. Okay, so anyway, getting back to track here. So the definition is that the Laplace transform of f is the integral from 0 to infinity of e to the minus st f of t dt. In my notes, I give a link to a video from an MIT professor who motivates this definition in terms of how it relates to another notion from discrete math. Most books don't even attempt to motivate this. It's really kind of a mysterious thing. I'm not going to try to motivate it today. I'm just telling you there is a link, and there is some answer to that question, but it's not a terribly easy answer. Okay, so that's the definition, and then I guess the question is, what are the Laplace transforms of things, right? So let's do a simple example. What's the Laplace transform of 1? And of course, this assumes that the Laplace transform exists. So we have e to the minus st over minus s evaluated from 0 to infinity. Of course, I mean a limit here, but this is, you know, e to the minus s times infinity over minus s. That goes to 0 for s greater than 0, right? And then we get plus 1 over s. So there you go. The Laplace transform of 1 is just 1 over s. Let's calculate the Laplace transform of an exponential. The Laplace transform of e to the, let's say, I don't know, lambda t. So integral from 0 to infinity of e to the minus st times e to the lambda t dt. So you see what you can do here. That's use laws of exponentials, right? This is integral 0 to infinity e to the minus, let's see here, minus, how would I do this? Minus s minus lambda, right? Times t dt. See what I did there? I got a plus lambda, but I did minus minus is plus. And then, well, this is a constant, right? So I can do the antiderivative in my head. Easy enough. It's minus e to the minus s minus lambda times t over s minus lambda, right? Evaluate from 0 to infinity. So we have minus e to the s minus lambda times infinity over s minus lambda plus 1 over s minus lambda, because when I plug in 0 and I use the minus from FTC part 2, there it is. Now, when will this term go away? What condition do we need between s and lambda? Not equal? Yeah. Well, if they're equal, it's 0. I guess it wouldn't go away. Well, yeah, if they're strictly equal, then this is a limiting thing, so it would, yeah. Right, I need this to be, for this to go to 0, I need that s is greater than lambda, basically. Yeah. That makes that a positive quantity, and so minus, I'm missing a minus, oops. That's kind of important. Duh. Oh, so there you go. I'm actually not being quite as lazy as I ought to be here, because I could have used example 1, we call this 1, to get example 2. Let me show you how. There's something called the Shift Theorem. The Shift Theorem cuts our work down considerably for Laplace transforms. Hey, Belu, is the sound still bouncing? Okay. All right, so where'd it go? Oh, shnikes. I don't see it. Well, I'll have to make it up. Theorem. The Laplace transform of e to the at times f of t is equal to the Laplace transform of f at s minus a. Or if I was to use a different notation, the Laplace transform of e to the at times f of t is equal to the Laplace transform of f evaluated at s minus a, okay? Sometimes I think this notation is clearer for this, but whatever. This is called the Shift Theorem. Now the proof of this and most everything else, it basically boils down to a simple calculus 2 calculation. It's so simple. I mean, it's so pretty. So Laplace transform of e to the at. Now I do have to assume that the Laplace transform of f exists, right? And there is a criteria that you could give to make that, to make it happen, to make it so. To quote a certain captain, if you can bound the function by like an exponential function of some particular degree, I think it's said to have exponential order alpha. I think if you have this, if you have like f of t, the absolute value that is less than or equal to e to the minus alpha t for all t bigger than something or something like that, then the function said to have exponential order alpha. In that case, it can be proved that the Laplace transform exists. So there's some, and if you look in the book, you'll see some discussion of this, but I'm trying to keep it short, so I won't say anything more about that. Okay, so this, excuse me, e to the minus st, e to the at, f of t dt, right? But what's that? That's the integral from 0 to infinity of e to the minus what? S minus a times t f of t dt, and that by definition is the Laplace transform of f at s minus a. Just replace s with s minus a, you can see it, right? Definition of Laplace transform, whatever goes here. Belu, can it see me over here? Whatever goes here, goes here. So I'm saying over here, I have s minus a, right? So that is, it's so simple, it's kind of, and so if you go back to example 1 and example 2, this is e to the lambda t times 1, right? So this says, you know, if this is f, then big F is equal to 1 over s, right? So f of s minus lambda is 1 over s minus lambda, and there you go. So simple, right? Now, for those of you who've had complex variables, or are about to, we can do more with example 2, right? What more can we do with example 2? I'm going to erase this. Is that okay? Belu, are we over here? So this, in fact, the Laplace transform extends to, you know, complex valued functions. Most complex variables books will have some chapter or section, at least, on Laplace transforms done in the complex domain. We don't need all that, but what we can do is we can look at example 2 complexified. So with lambda equals to alpha plus I beta for alpha and beta real, beta not equal to 0, right? And so the complexification, the Laplace transform of, let's say, y1 plus iy2, by definition, complexification works like L of y1 plus I times L of y2, right? That would be the complexified transform. Just that. We pull the I out in the natural way and force complex linearity. So in view of that, and also in view of the fact that complex calculus of a real variable works just like you'd like in the natural way, because the derivative of e to the lambda, you know, the critical thing is you can show that d dt of e to the alpha plus I beta times t is equal to alpha plus I beta times e to the alpha plus I beta times t, and understand that that's a rather complicated thing at purely real notation. That involves product rules of sines and cosines and exponential. There's a lot hidden in that statement. It doesn't come for free, but it's true. But because that's true, the integral calculus of complex exponentials works the same. And so what I get is this. I get the Laplace transform of e to the alpha plus I beta times t, right, at s is equal to 1 over s minus alpha minus I beta. Now that in and of itself isn't too interesting, but we can extract a real statement from this by multiplying by the conjugate. So you take this. I'll do the algebra in green. So this is s minus alpha plus I beta over s minus alpha plus I beta, right? And on the flip side, on the other side of this equation, this guy is what? That's really the Laplace transform of e to the alpha t cosine beta t plus I e to the alpha t sine beta t by Euler's formula, right? This gives me s minus alpha over s minus alpha quantity squared plus beta squared. Multiplying by the conjugate is intentional to remove the imaginary part from the denominator and leaves us with the magnitude, or the length, the complex plane of this number squared, the modulus squared, if you like, plus I times, well, beta over s minus alpha quantity squared plus beta squared. And so that shows me then that the Laplace transform of e to the alpha t cosine beta t is equal to s minus alpha over s minus alpha squared plus beta squared. Because again, I can break this up, right? I mean, there's one more step I haven't written down. Well, let me do it in red in the step above. Basically, I'm saying I can say, okay, so that's the Laplace transform of this plus I times the Laplace transform of that, right? And then I can say the real part has to match the real part, which I'll underline in purple, right? And then the imaginary part must match the imaginary part, which I'll underline in green. So all of a sudden, we know Laplace transforms of some of our favorite functions, constants, right? Sines, cosines, sines and cosines times exponentials, right? Exponentials. Hey, at this point we have the solution set to the homogeneous problem covered. Although I guess I need to do t to the n. Like, what's the Laplace transform of t? Right? Anyway, are we good on this? Yeah.
So then if we take away the exponential in front,
Right.
cosine,
Yeah, that's useful to note. The Laplace transform of just cosine beta t, it's simpler, right? It's, yeah. Right? And that's true. Oftentimes we just need that. Right, on the flip side, you could say, suppose beta is equal to 0 in this one, right? Then this will collapse to s minus alpha over s minus alpha squared, which of course is just 1 over s minus alpha, which we know from, yeah, I mean, there's other stuff to see in here, that's true. We good? All right, I'm going to move on then to the, let me come back over here actually. So the next theorem that I should prove for you guys is where is this thing? Yes, the Laplace transform. One thing I should say before I go on any further is it should be clear that the Laplace transform of c times f plus g is equal to the Laplace transform of f with a c out front plus the Laplace transform of g, right? That's one thing that I should, I should notice. We have linearity, right? I should have said that a long time ago, actually. That should have been one of the first things I said right after I wrote the definition. I lost my way. Forgive me. All right. Here's a less obvious thing. We can calculate what's the Laplace transform of, let's say, dy dt, right, at s. And we're also going to say we're given y of 0 is equal to y naught, okay? So let's work that out. So we have to take the integral from 0 to infinity, right? E to the minus st dy dt times dt, right? All right, so now here's the thing. If you look at ddt of e to the minus st times y, what do you get? You get minus s e to the minus st times y, right? Plus e to the minus st times dy dt. Product rule. So if you look at what we have, we've got this term, which is this term, right? So I can trade this for this guy minus that. But because there's a minus on that side, this gives me the integral from 0 to infinity, the total derivative of the product of e to the minus st and y, plus s e to the minus st times y. Again, y is an unknown function here, right? But we're assuming it has nice properties, like it's Laplace transformable. And now, okay, so this is the integral of a total derivative. So by the total change theorem, that's just e to the minus st y evaluated from 0 to infinity, right? And then plus, I can pull the s out, the integral from 0 to infinity of e to the minus st times y. And I can, the reason I can pull the s out is because this is integral over dt. The s is just a constant here, right? Excuse me. So at infinity, we get y of infinity, all right, times e to the minus s times infinity. So the e to the minus s times infinity should go to 0 pretty fast, right? If the y is also a nicely behaved function such that the exponential dominates it for some order, then this term has to be basically, it has to go to 0 at infinity. So given sufficiently decent conditions on y, this infinity goes to 0 in the evaluation, and we're just left with minus e to the 0 times y of 0. And what was this? Well, this is nothing more than s times the Laplace transform of y. And so there you go. That's what we got. We've got s times the Laplace transform of y minus y of 0. So let me just restate this theorem. The Laplace transform of y prime is equal to s times the Laplace transform of y minus y of 0. And there you go. So from integration by parts, actually, is what this is. We're just doing integration by parts. We have how to transform a derivative. But if you can do it once, you can do it again. What's the Laplace transform of y prime prime? Are you getting this, Belu? Are you sure? Right? So that's going to be s times, Laplace transform of y prime of 0, right? And that's s times s Laplace transform of y minus y of 0 minus y prime of 0. So you get s squared times Laplace transform of y minus s times y of 0 minus y prime of 0. So there's the Laplace transform of y prime prime. The other beautiful thing about this technique is it builds initial conditions into the solution. You don't have to fit initial conditions to a general solution later. You just build them in. If you want to find a general solution, you can just do the Laplace transform with respect to an arbitrary initial condition, if you like. That makes the algebra more difficult, but you can do it. Are we good? Okay, so that's how the derivative goes. Trying to think here what else I should show you in our short tour. Oh, yes, I should do the other one. What happens if you multiply t to the n times f? This is the other big theorem we need, is multiplication. We've seen differentiation in t becomes multiplication in s, right? See that? Differentiation in t becomes multiplication in the frequency domain. So what do you think happens with multiplication in t? What happens if we take, say, t to the n times f of t of s? What do you think? What should happen here? Let's see. We have integral from 0 to infinity, t to the n, f of t, e to the minus st dt. Maybe I should be lazier. Let's try for n equals 1. Let's not be too greedy. We'll just do n equals 1, see what happens. Maybe if we can do n equals 1, we can do n equals... Yeah, if we can do n equals 1, then we can do t squared by just successively applying the first one, right? Just like we did over here. Okay, so what? Any ideas? Here would be one thing I would make here's an observation. Notice ddt, dds rather, dds of e to the minus st is what?
Is it negative s?
It's what? E to the minus st times the dds of the inside, right? Which is what?
Just negative minus t.
Right. So look at what we have here. What do I have? Well, t is a constant with respect to the s differentiation, right? I mean, so you could look at this as the integral from 0 to infinity of what? We've got a t. It's really dds of what? Minus f of t e to the minus st dt. Because that differentiation pulls down the t, compensated with, well, minus t, and then the minus I put in there fixes it. The thing is, I'm assuming that t is independent from s, right? Exactly, yeah. So if we believe in things we can't if we're willing to take that wild, unjustified step of switching the order of integration and differentiation, as if that's allowed, in this case it is, then we have this, yeah. And there's a minus. But of course you can see what that is minus derivative with respect to s of the Laplace transform of f. Or if you want it in a more plain notation, the Laplace transform of t times y is equal to minus d big Y ds. What if we have t squared? T times ty, right? So that's minus dds of the Laplace transform of ty, right? Which is minus dds, yeah. Minus 1 squared y prime prime of s. In fact, generically speaking, you can see from this argument continuing that the Laplace transform of t to the n times y will be minus 1 to the n times the nth derivative of the big Y with respect to s. So now that we know that, we can easily calculate the Laplace transform of polynomials as they're generated from the Laplace transform of 1. Remember, the Laplace transform of 1. First example, 1 over s, right? So that says then that the Laplace transform of t is minus dds of 1 over s. 1 over s squared. And you recall the initial example, I assume that. Now we've showed it's true. Modulus of analysis, which we're not going to do. Laplace transform of t squared minus dds of 1 over s squared, right? Which is 2 over s cubed. et cetera, we get the Laplace transform of t to the n is n factorial over s to the n plus 1. This can be generalized in terms of the gamma function, right? The gamma function is a continuous extension of the factorial, right? So this becomes the Laplace transform of t to the n is equal to the gamma function of something divided by s to the n plus 1. I'm trying to remember gamma function of what. I don't think it's of n. I think it's gamma of n plus 1. That's the way it works. It's shifted a bit. So if you want to do for, say, n that's not an integer, you can refer to the gamma function, which is defined in terms of exponentials and things. I don't want to say anything more about that today. You can read about it. So this does have an extension to non-integer powers as well by the gamma function. All right. So that's those are your basic facts about Laplace transform. Now I need to go back to the unit step function. All right. Those are the basic tools you need to solve the problems we talked about basically for the first quarter or third of the course, right? You could use these things to solve the constant coefficient, problem. So now I need to talk about, suppose you have a function. I need to talk a little bit more about something. Suppose we have a function f of t, and it's defined in cases. I'm going to just do one of these examples, but suppose you have t squared for 0 less than t less than 1, and then the thing becomes sine t for 1 less than t less than pi, and then after that it's e to the t for t greater than pi, right? How can you write this in terms of unit step functions is my question. So here's the standard trick I'll share with you. The idea is to turn the t squared on at time 0. So t squared, how do I turn it on? Well, I can turn t squared on with u of t. That switches on to be 1 at time 0, right? Now this t squared, I want it to turn off. I want it to switch off when I get to time 1, right? So what I do then is I just subtract u of t minus 1. All right, so this thing you could call the gate function. If you wanted to, you could call it the gate function from 0 to 1 of t. Its graph is very boring. It's just non-zero right here from 1 to 0, like that. But that will give me the t squared that I want, and we'll put the t squared nowhere else. Mind its business, goes away. And then sine t, what I can do there, plus sine t. Well, if you understood what I said for the t squared, this will be no surprise. This is u of t minus 1 minus what? U of t minus pi, yeah. So this is the gate function from 1 to pi. Its graph is like non-zero just in here, right? And then, excuse me, you turn on e to the t, right, at time pi, and you never turn it off. So there you go. This is how to express a piecewise defined function in terms of sums of these unit step functions, right? And of course, you can see that we can do algebra to rewrite this. Like what? Belu, do we have this? This here too? Okay. So I can do algebra here, right? And I can collect terms. Like when I actually do the calculations, I want to rewrite it a little bit. I want t squared times u of t. And really, I can even drop this because we're assuming time starts at 0, so the u of t is kind of superfluous. It's not really needed. And then plus t squared. Well, t squared, I have... I'm sorry. Wrong way of thinking. Sine of t. I'm agreeing with you, but disagreeing. Minus t squared. I just like to write the function first and then the unit step function second. Just a matter of presentation, whatever, not a big deal. So then plus what? Plus e to the t minus sine t u of t minus pi. Now some people, when they teach the class, they will go straight to this step because they don't want to waste time on this intermediate step. For me, I have to do the intermediate step because I don't have room in my mind to memorize this thing. If I was doing it all the time, I would always jump straight to what's in blue. But the point is you can do it, right? So then we need to calculate what is the Laplace transform of something like, f of t times u of t minus a, right? And through essentially the same arguments we've been giving already, well, I'll just write it down. By definition, that would be the integral from 0 to infinity of f of t, u of t minus a, of course, e to the minus st dt. To get to the point, u of t minus a switches on at a, so basically that changes it from 0, changes the lower bound from 0 to a, and then this becomes 1 is a simple way to think of it, right? And then you've got integral from a to infinity of f of t e to the, and then so what you got to do is think about, okay, so I want to change this. I want to change this to see a Laplace transform, right? So to see a Laplace transform here, I need to get rid of this a. I need to switch a back to, I need to make that a be 0. So what change of variables should I do to make that happen? U equals to what? Yeah, u equals to t minus a will do it, I think. Then when t is equal to a, u is equal to 0. Right, so that's the integral from 0 to infinity. Now f of t becomes f of what? U plus a, right? And that's e to the minus s times u plus a. dt is du. And then you see, well, there's one extra e to, so what we get is e to the minus as times the Laplace transform of f of, well, t plus a, if you like it. I mean, using t or u is immaterial. It's a dummy variable of integration, so there's the rule. So unit step functions turn into multiplications by e to the minus as. And so if you turn this over, a lot of times you want to go the opposite direction. You want to calculate inverse Laplace transforms. So the other way around, if I want to say what's the Laplace inverse, let's see here, how do I say it? So if I have, let's try to think through this here. What if I have Laplace transform of g of t there, right? Times e to the minus as. What would that be equal to? Using the theorem we just proved with a substitution, let's say. So you say it'd be L of what? So you're saying, let me just write it out. This is, we're thinking of that as being the f of t plus a, right? So I'm supposed to put f of, I'll just write it down again here, f of t, oh, maybe I shouldn't do that. Sorry. G of t minus a, right. If that becomes t, then it must have been t minus a over here, since we have to add a and u of t minus a. I think it'd just be u of t minus a because it's not, I'm not messing with this, which is where that came from, the unit step functions, where the e minus a is from. Let's see here. I'm not entirely certain I've written it in the right format just yet. So yeah, okay. I mean, this is a useful result, right? So this says that. Let me just rewrite it one more time. This is e to the minus as times f of s, right? Is equal to, what is it? The Laplace transform of f of t minus a times u of t minus a. Or if you take the inverse Laplace transform of both sides, you have the inverse Laplace transform of e to the minus as times f of s of t is just equal to f of t minus a u of t minus a. More often than not, what I just wrote down is what we actually need to use when we're taking the inverse Laplace transform. This, of course, over here, is what we need to use when we're taking the Laplace transform. And we need both of those relations to make it work. Is good? All right. Excuse me. Goodness gracious. Okay. So then the question then becomes, that's most of it. Now we should talk more about how to actually calculate inverse Laplace transforms a little bit, all right? So I've shown you how to take Laplace transforms. The question is, how do you take the inverse Laplace transform? Well, you just undo it, right? Well, yeah. Sometimes that's easy. So let's do some easy examples. So inverse Laplace transform of 1 over s plus s over s squared plus 1 plus 1 over s squared plus 2. That's reasonably easy. 1 over s, inverse transform. 1, example 1 done backwards, right? This was cosine t. And I'm using linearity. The inverse transform is linear as well. This right here isn't quite what you want. See, because in order to see it as one of the things we found already, I need to write the 2 as the square root of 2 squared. Right? And this 1 is not what I need either, right? So I need to do some kind of I need to use my imagination a little bit. I can rewrite this as the square root of 2 times 1 over the square root of 2. Aha! Now that is a sine of square root of 2t. So I get plus 1 over the square root of 2 times sine the square root of 2t. But there you go. Right. Another example. Inverse Laplace transform of 1 over s squared minus 1. You're like, that was not on our list. That is true. But through a little algebra that we know and love from Calculus 2, called partial fractions, this one is 1/2, 1 over something, I think s plus 1? No, maybe s, I think it's s minus 1. 1/2 of s minus 1 plus 1/2 of s plus 1. Of course, what did I just do? I did reverse common denominatoring, right? Partial fractions. Is it right? Well, make it a common denominator it, if you like. So this is s plus 1. That's s minus 1 when I cross multiply, and so I get s plus s gives me 2s. Uh-oh. Yeah, you're right. I need to minus. Phooey. Is it in the right order? Then I have s plus 1. Yeah. Then I use linearity, right? It's 1/2 inverse Laplace transform of 1 over s minus 1 minus 1/2 inverse Laplace transform of 1 over s plus 1. What's that? Well, that's 1/2 e to the t minus 1/2 e to the minus t. Belu, can we see that over there? All right. Now, do you guys recognize what this is? Yeah, that's sinh of t, which is in fact very, very satisfying, right? Because if I change this to a plus, I get sine t. With a minus, I get sinh t. In fact, you can prove that the Laplace transform of e to the alpha t sinh beta t is equal to beta divided by s minus alpha squared, and here's the difference, minus beta squared. And likewise, cosh, same thing, but with s minus alpha upstairs. So very natural, the interplay between sine, cosine, and cosh and sinh. But you see, to undo these kinds of things, we're going to need partial fractions, right? Let me show you an example. So rather than just doing inverse transforms, let's actually solve a problem. Then we're almost done with this. So can I erase? Well, not yet, maybe. Maybe not yet. I'll go over here. By the way, the actual details of Laplace transforming one of these things that I'm just erasing, it will take you, you need to spend an hour or two on it at least, kind of work out the kinks there. You'll eventually need like adding angles formulas and different things to see through certain problems. There's subtleties in the calculus and algebra there. Okay, so for example, suppose I want to solve y prime prime plus 3y prime plus 2y is equal to, let's see here, to make it interesting, the unit step function of t minus 2. So, and I'm to keep life simple, I'm going to assume that y of 0 is equal to y prime of 0 is equal to 0. That will cut down the algebraic difficulty slightly. Because basically that's making the homogeneous solution go away. So I take the Laplace transform of this. That gives me s squared big Y plus 3s big Y plus 2 times big Y equals to 1 over s times times e to the minus 2s, if I recall correctly, right? So what I do, I took the Laplace transform. Now what always happens for these problems is you'll pull out the characteristic polynomial in s. So s squared plus 3s plus 2y equals 1 over s e to the minus 2s. Now I need to solve for big Y. Big Y equals 1 over s times, well, what is this really? It's really s plus 1 times s plus 2, right? I'm just going ahead and making that observation for my next step's convenience. So I'm done with step 2 in the 3-step process I described. Now what do I have to do? I have to take the inverse transform of this, right? So if I call this thing, say, f of s, then I know that my y of t will be the inverse Laplace transform of f of s times e to the minus 2s, right? And I know what that is. That's f of t minus 2 times u of t minus 2, which intuitively makes so much sense. If I'm assuming that the initial condition is 0 and 0, what that says is the y just sits there at 0 until time 2, when it responds to the forcing function turning on at time 2. Now I don't know what that response is yet because I still haven't calculated the inverse Laplace transform of big F. But you see now I can ignore the exponential and focus on the algebra of f, big F of s. So, but that's partial fractions. And the reason we do partial fractions is because by doing partial fractions, I take this thing I don't know how to take the inverse Laplace transform of, and I'm going to replace it with something like this, which I do know how to do partial fractions, inverse transform for.